Hi, this is part 2 of the course introduction. And this video lesson will introduce the interdisciplinary methods and concepts that we'll use to frame the study of the specific topics in the course. And we'll conclude with the goals and the learning outcomes that you can work toward through the course. First, just a big picture overview of our interdisciplinary knowledge base. There's a great base of concepts and methods that we'll draw from. We'll be studying some of these explicitly, but most of the time these interdisciplinary approaches will be integrated with the content of each of the syllabus units in the course. And in this lesson I'll go over what these great intellectual resources provide as we think through the best ways to understand our key technologies. The first is complexity and systems thinking and network thinking, which emerges from it. And this great body of conceptualization and research provides the ways of modeling questions with a systems and network paradigm. This has been one of the most powerful research paradigms in the modern world, and you could say that so much has emerged from it. The systems and complexity assumptions are woven through and unite many sciences and engineering with fields like linguistics, semiotics, and communications, computation, network theory of all kinds, and the study of all kinds of systems, complex systems like social and economic and political. And it's good to have a sense of what the foundational assumptions are, because when you get an intuitive sense of what the foundational concepts are, you'll see how you can extend and apply them to many other areas. We'll start with a great quotation by Gregory Bateson, one of the founders of cybernetics and a really important systems thinker himself. What can be studied is always a relationship or an infinite regress of relationships and never a thing. So we begin with the premise that whatever it is that we're studying in a complex system has to be studied in its position as a node in a system of relationships, as opposed to something that you can isolate and investigate and analyze independently of the system. So when we define a system in this scientific sense, we find that we begin by conceptualizing it as a relational structure of interconnected, interdependent constituent elements that are defined in their relations and actions that emerge from within the system itself. And in most complex systems analysis, the method usually proceeds by breaking things down into decomposable units. We can call them subsystems, subprocesses, or constituent units that exist only in their interrelations. You can't tease it out and study things independently of the system. And each subsystem in a network can work semi-autonomously without requiring information about other system components or about the structure of the system as a whole. And we can see how this works in things like social networks, where you can be part of a group or an organization or a network of friends who know other friends, and no one person within a group or in a social network of friends and acquaintances needs to know what all the members individually are doing in the social organization, for each of them to have their role and position within the social structure itself. The same thing in a complex system like the internet, our great model for a network of networks. No node within the internet system needs to know what's going on in other parts of the network for each of the component nodes within the internet to work within the system as a whole. The dominant conceptual metaphor of systems thinking is the network, and this is such a great, powerful modeling concept. We see this applied in so many areas. It first emerged in mathematics and other kinds of system thinking because a network can be modeled in a graph of linked nodes. And when you model it this way, you get a picture of how all these interdependencies work, and that the network becomes defined as a set of these relations as opposed to something that you can extract out and interpret and analyze independently. And this is such a great modeling concept, extensible across many fields. I'm sure many of you have come across this in other kinds of fields of research already. Design thinking, another really powerful body of approaches, paradigms, concepts, and methods that we'll be drawing from. And there's many approaches and schools of thought in the discipline you might call design, or the different fields that use design thinking. We're going to be looking at three key sources and integrate them into our approaches in the course. Modular design principles. So much of our complex technical systems today are developed by modular design, how components can be structured in layers and levels of combination, and how the modules have to be designed to be interoperable, to work together as part of a whole. Cumulative combinatoriality and the extensibility of combination. Most of our key technologies, especially the ones we're studying in media, computation, communication, exist by combining and summing up prior combinations of technologies. And this is extensible and scalable for the future. Human-computer interaction, very important principles that are summed up in a lot of ways in which interfaces are designed, interactions between hardware and software, and the design principles for designing technology to be able to correspond to what's actually possible for humans to do in these relations. Well, the implementations of all of these design principles are around us all the time, and we're always figuring out ways to orchestrate these interconnected components and complex systems and computing devices and airplanes. I mean, contemporary airplanes are just an amazing combinatorial design. So many components and subcomponents and systems, it's hard to even know what the referent of the term airplane is, because it's such a complex hybrid of technologies and agencies. Cars, too. I mean, it's common knowledge that there's more computing power in our cars today than in the Apollo spaceships. Our cars are basically local area networks run by electronics and hybrid systems of mechanical and electronic and navigational components. The internet, of course, one of the best paradigms for a complex design system that can only work by orchestrating modular design and various kinds of layers and levels in which the network interacts. And of course, all implementations of software require this kind of design thinking in which layers and levels can be modeled and implemented, and the inputs and outputs of various layers can be passed on to others within the whole software system. Well, we find that all these kinds of thinking are implemented and used and applied in so many things around us every day. But the really interesting thing about it, for me, is that these provide really generative and creative principles that are behind a lot of the key technologies we experience every day. There's a great quotation from Brian Arthur, who we'll be reading and studying this week and next. A complexity thinker who's done some really interesting work on insights in how new technologies emerge from the summing of combinations from prior technologies. If new technologies are indeed combinations of previous ones, then the stock of existing technologies must somehow provide the parts for combination. So the very accumulation of early technologies begets further accumulation. New technologies are constructed mentally before they're constructed physically. Novel technologies issue forth from the collective of existing ones. Incredibly perceptive statements in Arthur's work, and this sense that new technologies emerge as conceptual machines first before they're implemented as physical ones, because of this fundamental design process that motivates the composition of all of our complex technologies. So combinatorial design reveals that an inherited design is always already a cumulative summation of prior histories of combinatorial design, which then motivates further combination as component technologies are developed with combinatoriality built in. And this is one of the great principles of extensibility and scalability that we find that so many of our computationally based technologies are based on. And when we look at our paradigm case of the iPhone 5, which we'll be looking at as a case study throughout the course, we find so many of these design principles are implemented and are really, I think, very visible for us to unpack and to understand, because mobile devices, iPhones, are such a great example of how this combinatorial principle can work and what it is to be able to integrate and combine in all of these modular layers. Here's an interesting diagram. It's mostly, of course, from an industry point of view. It's not as conceptual as we could work with, but it does provide an interesting map of looking at the iPhone as this combinatorial hybrid or summation of a lot of these other kinds of devices, but more, if we look at it more as the combination of functions. The great value add of iPhones and other devices was this integrative bundling of prior functions that hadn't been combined and bundled in the same way in one platform before. And we're going to be looking at this as a case study and many other combinatorially designed devices for how this principle works and how you can work with these ideas to understand and interpret new technologies as they emerge. Computational thinking, of course, a key to so much of the media, computational, and information world that we're around. And computer scientists today who are working on how to teach computer science ideas, how to get more and more people involved, are finding that at the core, computational thinking underlies so many other important thought processes. And it's not just the same as what many people think are the instrumental value of learning programming, but computational thinking precedes programming. And the more we understand what it is about computational thinking that we can implement and create designs for in all of our information and communication technologies, the more we'll have insight into how things are possible, how things come to be. Computational thinking is primarily an extrapolation from and formalization of core human cognitive abilities in symbolic thought for modeling and abstraction. So we're back to this primary fundamental principle that everything in computation, symbolic representation, information is an extension of core human processes, not autonomous functions of machines. And we use these methods for defining the methods to map formalizable symbolic structures onto automated processes that can be represented in programs. There's where the writing of actual programs comes in, and implemented in a computer system. It has to be implemented in a specific device or physical system, of course. But note that it's about designing human interaction with purposive machine processes for extending human capabilities and social functions. So at core, computation is, according to my friend and colleague Peter Denning in ACM, really about information transformation. And the more we understand what that is, how we're able to do it, the more we're able to really get at what these core computational processes are. So to map these out, and I'm going to go through the kinds of conceptual and analytical processes behind computation very quickly here. We'll cover it later in the syllabus, but I just wanted you to have a big picture overview of it at this point, and to make it as intuitively clear. But don't be worried if it all doesn't make sense now, because we will be covering it later. But just so that you have a picture of, okay, what do computer scientists mean when they're talking about computation, or what is computational thinking in the largest sense? What do we have to engage to make this happen? Well, first of all is abstraction. a key component of all human conceptualization, and the ability to work with symbols and to allow symbols to represent other symbols and other layers and orders of abstraction. Computation engages this fundamentally. As we've seen in modular thinking, computation also has to work by decomposition and composition. That is, how do you take a complex problem or process and break it into the constituent components needed, or the steps needed to actually execute it. Algorithmic thinking, essential, because this is how we model and represent the steps in a computational process that are like a recipe that can be translated into an actual programming language that can be executed in a machine. This is back to Brian Arthur's point that an abstract machine always precedes the physical one. We model it conceptually first before we can implement it physically. Pattern recognition. We see this every day, every time you do a Google search, every time you launch an app. It involves sorting, categorizing, indexing, using search methods to be able to sort through massive amounts of data. Without key pattern recognition processes, we wouldn't be able to do any of this. And we're also finding out that computation engages this collaborative and collective thinking process that's been part of human knowledge building and social relations for as far back as we can go. Computation models information processes that are necessarily collective and collaborative. It's about building cognitive networks of people and computers, and we're going to explore more of the implications of this in the course in the unit on computation. Well, we know computation is everywhere, and we know that computing now rarely looks like a computer. Computer processes are built in everywhere. They're embedded in the environment, and sensors and TVs and cars, all of our entertainment equipment, traffic lights, appliances. So learning the fundamentals of computational design concepts opens up ways to understand our everyday technology environment and its future. And the more you can understand, the more you'll be able to participate in that future. So let's look at a couple of interesting cases, how, kind of large scale, how this design thinking, computational thinking helps us to understand how we get these scalable, complex systems like cloud computing, the Internet of Things. It reminds me of a great slogan that Vint Cerf, one of the important founders of the Internet and who now is the technology evangelist at Google, a great T-shirt that said IP on everything, which means Internet protocol on everything. The dream to have Internet addressable everything, people, devices, sensors, locations. Well, that was an interesting dream 20 years ago, and of course now it's more a reality. We have so many ways of creating what we call the Internet of Things, where we have Internet addressable devices and devices that we carry or that we wear or that are in sensors in our built environment. And we're predicting that by around 2020, there'll probably be about 37 billion intelligent things connected to the Internet. This is going to create a world of massive communication, information, intelligence, and data. And the more we can learn about how this is designable from the principles that we've been discussing, the more it will be understandable to people who won't directly be involved in the engineering. And as Cisco, these infographics, the company Cisco, who is so important in the equipment for the infrastructure of the Internet that we use every day, is pointing out in their marketing that it's all about connecting everything, people, processes, data and things, that this is where we envision the Internet going, and it's pretty much getting there and implementable already. Now, another major school of thought that we'll be drawing from throughout the course is the sociology and social history of science and technology. This is a large interdisciplinary field which involves the social science applications of systems and network thinking. And the major schools of thought are actor network theory, science and technology studies, mediology, and many others. People who work across disciplines in social sciences and information sciences and communication and engineering. It's a pretty large overlapping field and kind of hard to just name specifically. There's an important concept that emerges from this of distributed agency, and it's part of thinking through how social and technical institutional systems are really about propagating and distributing agency, that is, means for action, power, authority, ability to act within the system. And we're finding that this happens through the distribution of agency in heterogeneous networks. That is, we have the network system of people, groups, and institutions, technologies that mediate this kinds of agency and implement it, and technologies that delegate human agency, both individual and collective and group. Well, the social science applications of systems and network theory help us break through two related problems that I've always appreciated for how to think through this. Questions of causality and agency in technology are redefined in interdependent social technical relations of distributed agency. And as we saw in the first part of the introduction, how important it is to the starting point of beginning to understand technologies, and the technologies we're focusing on, is to do away with naive determinism, linear causality, and think about these systemic networks, these networks of distributed agency, where we find that there's so many participants and so many points of mediation. This enables us to reverse this black box effect that we talk about a lot. The more a complex technology becomes highly adopted, like PCs and mobile devices, the more the products become totalized and unified and opaque to users, who are closed off from understanding what it takes to make a technology work in the combined agency of many interdependent technologies, industries, and institutions. So we're going to want to work with these ideas. They're very heuristic. That is, they help us make discoveries and see things that we couldn't otherwise see. Well, I want to return to a concrete case again, the iPhone, and I just want to walk you through how we can use some of these insights that I've discussed so far in this part 2 of the video introduction to de-black box components of the iPhone. Now, if we open up an iPhone and look at physical components, right, you're going to see a really complex set of components in the component board. And one of the first things we can do when we look at these components is to not just stop at them as material technologies, right, but to ask the big questions about them, to say, well, actually, these material components are interfaces to the whole system that made them possible. And the system that made them possible is not technical, is not necessarily technological. The system that made them possible is social, it's economic, it's institutional, it's political. A whole set of forces and agencies have to combine. And we're going to look specifically at this Qualcomm chipset just for a minute, because those of us who have mobile devices, we're using these all day long, right? We don't really understand the cascading effects of processes that we initiate when we send and receive digital data, when we make a phone call. But when we look at these chips in the chipboard, complex combinatorial relation with everything else going on, right, we realize that this isn't just opaque hardware, right? It's not a matter of looking at this from a geek point of view, which is cool enough. I mean, the design of the boards are pretty cool to look at. But each component represents an interface to the larger social technical system that makes it possible. None of which come from Apple. And this is the point that I make, frequently, that what we can't see is always the most powerful. So what enables the wireless functions that we enact in any mobile device? So let's just use the chip as an interface. What is it an interface to? Well, you can describe the technical material interfaces, within the iPhone circuit board, but that doesn't explain how it came to be, what makes it powerful, what gives it the ability to operate outside its own little black box. Well, actually, it's an interface to all these other elements of this complex social technical network that make the wireless chip function the way it does. Everything behind the scenes on standards, on policy, wireless chip design, agreements about radio frequency, agreements about how you design a chip to interact with all of these prior technical social standards that are already in place. That precedes any function that we're able to enact in the chip. So just think about that for a while, and we'll return to it at the end. The other important concept base are the sciences of cognition, communication, and meaning. A large interrelated, interdisciplinary set of fields that are now uniting around this question of what it is about human cognition and thought and conceptualizing in symbols. Communication and information processes are forms of symbol representation and processing and transformation. And all human collective symbol systems are based on a common structure, and if you've had courses in communications or linguistics or semiotics, you've probably come across these foundational principles before, that any symbol system has to contain this structure, components in this structure. Perceptible signifiers, learned associated contents, rules for combining units in a syntax, and the cognitive processes for generating additional meanings that are expressible in only in further strings of symbols. So understood in the larger context of human meaning systems, all of our symbolic systems and modes of communication are used for meaning generation. So the big question that unites cognitive and computational sciences is, what are the unifying cognitive principles that enable us to create abstract symbolic operations on strings of symbols, one way of defining computations, that yield results as other strings of symbols with additional meaning or value? I should note that this is another approach which erases this human-machine dichotomy. Instead, we find that technologies are forms of extended and distributed cognition, methods for offloading cognitive tasks that no one mind could perform for collective human thought and action. Media theory and new media studies is another major field that we'll be drawing many important concepts and methods from. The field provides all kinds of great resources for studying media both on the macro and the micro levels. And traditions in this field begin with people like Marshall McLuhan and people thinking through the nature of media in the electronic age. And this field has gone through many transformations as media have developed in the modern world and as industries have developed around them. And if you've studied in this field before, you know we've inherited approaches and methods for studying the history of media and all the industries around them. All of media history, news media, mass media, material media formats, and the industries around them. So this provides an incredibly rich resource base for the study of media history and the concepts around what media is and all of its manifestations and implementations. And today we're in an environment where we're noticing the reconfiguration of media through digitization and digital platforms. And we have a continually reconfiguring media system across many industries. And one of the major consequences of digitization have been this new configuration around two kinds of digital forms. One which we call traditional media remediated, that is, the industries that are now reconfigured around the traditional forms that we've had for many centuries, but now in a digital form. And now the born digital media, that is, media created totally in software and delivered over computer networks and displayed in digital media formats on our screens and our digital media decoders for audio and video. The internet and digital media have prompted new kinds of questions in many research communities that span this large interdisciplinary field. And I'm really interested by what kinds of new questions that we're prompted to ask, especially now that we can get at the history of media and all of its functions in new ways. We're asking these big questions like how and what do media mediate in all dimensions of the term? Marshall McLuhan was great at getting this question started by continuing to emphasize that the television has much more power and much more influence than any specific content, any particular program, that the medium of television itself had such a pervasive influence over the world. And obviously today, computers, computing devices, digital media have far more power and influence in the world and in our lives than the content of any specific thing transmitted over these devices or displayed on them, or the actual use of any specific app or software. And we're asking, what are the differences and continuities in the history of media? What are the differences, and do they matter in analog media and digital media? And through digitization, what happens in the remediation of earlier forms? Radio, television, print, and text. These are still with us. In fact, in many ways, they're with us more than ever before. There's more text messages sent around the world than we've ever seen before in terms of text as a medium. And what is different about media born digital? That is, media that is created totally in software and only displayed and used and consumed in digital form. And what is the materiality of a digital media object? So often we think about digital things as abstract, disembodied states, but actually they're very physical. They take physical forms of memory. They have to be displayed on physical devices. They have to be decoded back into the analog form. We always live in an analog world. We have to perceive the media that we create and consume. Well, I'd like to conclude with a thought experiment that will help you get oriented to the kinds of questions that we're going to ask in the course. And having gone through some of the ideas in this introduction and the framing, the intellectual resources that we're going to draw on to understand our technologies, the next time you touch an app icon on your mobile device or click on a link in your web browser, just pull back for a minute and think about the implemented designs for the combinatorial technologies that are going on. We'll be talking about this a lot in the course, and I'll be trying to give you the tools to think with to really get at these questions. But just start going through in your own mind what it would take to think through these questions. How can we discover what it takes to make the combined features and functions work in the user interface? Obviously, the manufacturers give us these great, shiny, productized black boxes, and they want us to be caught up on how cool they are and slick they are, and of course they are, but they are still closed off. They still don't allow us access to understand what it is about the technologies and how everything in the background has to be orchestrated to make the functions we perceive work the way they do. How can we discover and understand the underlying system of unobservable dependencies? These are both technical, social, and of course the network of all other kinds of forces that we know, institutional, political, and economic, that make the observable functions work. So let's just briefly sum up our learning goals and outcomes for the course. By the end of the course, you'll be able to work with your own toolkit of concepts, methods, and background knowledge that you can apply to any technology question by applying the key concepts and design principles that make our technologies possible and extensible for future development. Your goal is to learn the concepts and methods that will allow you to keep on learning and enable you to participate in important technology-related issues in your own field. This concludes part 2 of the introduction to key concepts in technology, and this is the conclusion of the introduction to the course as a whole. I really look forward to working with you online in the course and for helping you to build your own knowledge base for for how to understand the key technologies of our own time.